All right, so continuing to discuss the problem of coordinate change for the matrix of a linear transformation, we now focus our attention on the case that we're going from column vectors to column vectors. This is an important and common case that we have a lot of time in this course devoted to, actually, as we go on past this point. So basically the problem here is we have a linear transformation from Fn to Fm. We got two pairs of basis, beta and beta bar, gamma and gamma bar. So in this context, of course, we can talk about the basis matrix, either m by n, or m by m, or n by n, right? And I would also point out that we can do some kind of neat calculations like this. I'm actually going to go ahead and derive, oops, sorry about that, derive the coordinate change formula here directly in terms of some little matrix calculations. I think it's instructive. Of course, you could just go back to my general derivation and specialize it to this context. I think it's probably what I have in the notes. But here, t of x is equal to the standard matrix of t times x. And of course, we can insert beta bar and beta bar inverse like that. You recognize at this point that that's the coordinate vector of x, right? So let me write one more step here. This is actually equal to standard matrix of t times the beta matrix times the coordinate vector of x with respect to the beta basis, right? But on the other hand, the image t of x is in Fm, so we can also expand that in terms of the gamma coordinates, right? So this would be gamma times the gamma coordinate vector of the image, right? So we can put these things together, and putting them together, we get that gamma times the coordinate vector of t of x with respect to the gamma basis is equal to the standard matrix of t times the beta basis times the coordinate vector of x. All right, well, so what? Well then, if you multiply this by the inverse of the gamma matrix on both sides, we get that the image is equal to gamma inverse t beta, x beta again. But on the flip side, this by definition is the matrix of t beta gamma times the coordinate vector of x with respect to beta. This has to be equal. It holds for all x, so it holds for all coordinate vectors, which means we can peel off the x beta, and we discover the formula right here, which is nice and special to column vectors, which is if you want to change from the standard basis to a non-standard basis for linear transformation, simply multiply by the inverse of the basis matrix in the codomain times the basis matrix in the domain on your standard matrix. But then the thing is, if I can do that, oh my goodness, my apologies, Benjamin is trying to add his own percussion to this video. In any event, this calculation just as well holds for the barred basis, right? And so I can just as well calculate that the t with bars is equal to gamma bar inverse t beta bar. But the thing is, the standard basis is unique, so we can meet these in the middle and make them both, solve for standard matrix both of these equations, this equation and the other circled red equation. And when we do that, we get standard matrix is equal to this is equal to that. And then, of course, I can take this and I can solve for the barred basis, and there you go. That's the formula. The relation of the standard matrix, not the standard, rather, the matrix of linear transformation of column vectors with respect to different choice of base, beta bar versus gamma bar. Now there's a big difference between this and the formula we looked at before. Now I actually have 1, 2, 3, 4, 5 different matrices being multiplied. Before the coordinate change formula, I just had the matrix of like p gamma bar here and p beta bar inverse over here. It was not further decomposed into a product of matrices. The reason that happens here is, of course, because we're in column vectors and things simplify a bit there. So here's a good example. Where'd my good example go? I had a good example. I have somehow lost it. Where'd it go? No, it's not it. Uno momento. Por favor. Ah, here it is. Here we go. So here's the formula I was just talking about written nicely. There's the relation between the barred and the unbarred matrix. Now, and of course, even more special is that when we have, when we're relating to the standard matrix, then we just get to do this. Oftentimes we do that. So here's an example. And also, this example is important because it gives you some sense of, why do we care about coordinate change anyway? So here's the example. And so I'm looking at a linear transformation on R3. And its formula, t of x by z, 2x minus 2y, 2z, x minus z, 2x minus 3y minus 2z. So it clearly has the standard matrix 2 minus 2, 2, 1, 0 minus 1, 2 minus 3, 2, right? And then I can calculate the matrix with respect to the beta bar basis by simply doing this transformation, multiplying by... Now here, this is actually a still more special case because you notice here I'm looking at t going from R3 to R3, and I've actually given both the domain and the codomain basis beta. Alright, so this up here specializes to, beta, well, I guess I call them bars just to be more in tune with my notation up here. So beta bar inverse standard matrix T beta bar like that. So in the special case that we're just giving the same domain to the range and the codomain and the domain, then we just multiply by the matrix and its inverse for the basis matrix. I do not show you the details, but the inverse of that basis matrix is actually this. Fascinating, yes. And so multiplying that by that, we get this, and then we get that. And so this, by the way, makes beta bar what's called an eigenbasis. The reason it's called an eigenbasis is because if you look at it, t of 1, 0, 1 is actually equal to 4 times 1, 0, 1. Right? T of 0, 1, 1 is actually equal to minus 0, 1, 1. And t of 4, 3, 1 is actually equal to 4, 3, 1 again. So in other words, we've got an eigenvalue of 4, an eigenvalue of minus 1, and an eigenvalue of 1 as it happens. And you see what happens, converting from the standard basis to the eigenbasis does what to this linear transformation? It reveals that in the eigencoordinate system, if I was to write the formula for it, like t, let's say t tilde of x bar, y bar, z bar, where those are the eigencoordinates. Well, the eigencoordinates formula for this is really kind of silly. It's, it's just 4x bar minus y bar z bar. Yeah. In terms of eigencoordinates, that's what the formula for t bar looks like. Right? I'm saying t tilde. I say t tilde because technically speaking, it's not t anymore. But okay. Anyway, with this change of notation, the formula so simplifies, and it reveals the true nature of this linear transformation, which is that it's taking one direction and like dilating it by a factor of 4. It's flipping the other direction over, and it's just fixing the 4, 3, 1 direction. So we have a lot more to say about eigenvectors in the next story arc in the course. We're not quite there yet, but coordinate change, of course, is a very important part of that. And I would just point out that, if we have t, right, going from a vector space V to itself, right, then if we use basis beta here and we use this basis beta there, we use the same basis in the domain and codomain. So we could study beta bar and beta bar here, right? Then how is the matrix of T with respect to beta bar beta related to, the matrix of T with respect to the beta matrix? Well, going back to what we did before, it's just this, right? So you might recognize this. This is a similarity transformation, right? So with this in view, it all of a sudden makes sense to define for a linear transformation things which are invariant under similarity transformation. This gives us license to define things like, for example, the determinant of T. It now makes sense to say, well, the determinant of T is just the determinant of the matrix of T with respect to a basis, beta. Because it doesn't matter which basis you pick, they all give you the same determinant, right? Because if I change to the bar basis, well, it gives you the same determinant. And we can define the trace of a linear transformation for the same reason, because the trace can't tell the difference. You know, if I take P, T beta beta, P inverse, in other words, if I define the trace in terms of T beta bar, well, by properties of trace, that's the same as the trace of T beta beta. So it doesn't matter which basis I use to define the trace, any one will invariantly define the trace of a linear transformation. And there are other things, like we can define, you know, the rank of the linear transformation. We can define the nullity of a linear transformation. So rank is the dimension of the range of T, right? But it's also the dimension of the column space of the matrix of T with respect to any basis, as it happens here. And this is the dimension of the null space. But as we have discussed in other theorems, that's also the dimension of the null space of T. And I had a more general theorem in the notes that didn't assume that the domain and codomain were both the same vector space. But in the case that they are, the column space for one choice of matrix and another choice of matrix, those different matrix representing T's would be related by a similarity transformation. So there it's especially easy to see that the rank, I mean the number of columns of similar matrices that are linearly independent are the same. Anyway, let me stop. But so next up we should talk about the relation between the dimension, the rank versus the nullity of the matrix. So there's a simple little theorem that we should prove. If I have time today, I'll prove it. I need to go count my minutes and see if I have any left. Thanks, guys.